Thank you, Andreas. And also thank you guys for staying till 7 o'clock. It's pretty late by conference standard. So tell you a bit more about myself. Until, like Andreas said, until recently, I've been working for a company called Gamesys in London for the past almost 6 years. And during which a lot of my time I've been working with .NET Stack with both C# and F#, but also some Erlang as well. And pretty much most of the things that I write gets run on Amazon Web Services. And we also have a couple of services that are hosted in Google App Engine. And we use a whole host of different languages at work, as well as databases and cloud platforms. And in today's talk, I want to talk about some of the cases, well, some of the use cases that I found for F# in my line of work in terms of writing backends to support social games for millions of players. And none of the things I'm going to be talking about is particularly difficult or technically very challenging. But I think that's kind of the point I'm trying to get across, that even if you're doing sort of line of business applications, the things that you tend to do day to day in terms of domain modeling, writing some business logic or some algorithms, all of those things are wins that you can sell to your colleagues and friends who maybe haven't bought into the functional programming way of thinking. And just to give you some context as well, so the games I've been working on, as of October, when I left the company at the start of this month, we had around 1 million daily active users coming to our games every day. And between them, they generate somewhere around 250 million requests per day. So these are not small systems. They are fairly large, scalable systems that are running in production for quite a number of years now, and they get hit all the time. So how did we came to F#? Well, I've been a big fan of F# since the very early days, but I had to sort of buy my time and wait for the right use cases to come up before I was able to push it into our stack. And you see in some examples, I'm going to show you how, in our experience, using F# has given us a lot of productivity increase, helping us to do things quicker and get to market on a timely basis, at the same time without sacrificing on quality and building applications that behave correctly. And in certain cases where we need to write concurrent and parallel code, we also find that F# is a very good tool for us to write very efficient code to do that. And often, and this is one of my personal favorites for using F# is that I can often come up with simple solutions to problems that other people may consider as complex. And I hope as functional programmers that are doing functional programming work day to day, you will probably sympathize with a lot of these points I'm going to make. And as a company, Gamesys is very well known for the sort of real money gambling products that they make. And in my team, we build social casino and social slots games. That's where most of our revenues are coming from. And as an example, this game is one of the more popular games that we have ever done in the company. It's kind of clipped at the bottom there. And if you haven't played a slots game before, I don't blame you. It's not something that I have ever done in my life until I started working on them. Sorry about that. Keep getting this pop-up. Let me just fix it once and for all. Turn off Wi-Fi. There you go. So in terms of the game mechanic for slots games, it's very simple. You decide on your wager and how many of these sort of lines that you want to bet on. And then when you press spin, the wheel's going to spin. And once they settle down, the symbols that land, you can get what is called a line win if you got matching symbols and along any of these pay lines. Or in this particular game, if you get 3 or more bonus symbols anywhere on the screen, because it's not associated with a pay line, that's why they call a scatter win. And behind the scenes, on the backend side, every game has got a math model that ultimately determines your chance of winning, how much you're going to win for different combinations of symbols, and so on and so forth. And for this game, there's also a special feature that as you are playing, you collect those tokens from the classic Monopoly games, so that when you go into the bonus game, we give you a classic Monopoly board where you can place those tokens on the board to help you do better in the bonus game. So to model the domain for this game, we can use what is called a union type to represent the different symbols you can have. If you're coming from Java or C#, think of this as like a tagged enum where each of the cases can be associated with an arbitrary set of types. So here we are saying that a standard symbol has to be instantiated with a string, whereas a while symbol is just what it says on the tin. We can do the same thing to model the different wins we can have, which is either a payline win with the payline number, the symbol, and the number of symbols that we've won, or a scattered win with just a symbol and count. And something that I always do myself is to use a type alias to help surface my domain through my type signatures. It's all well and good having integers and strings and whatnot, but that's what my domain is all about. My domain is about paylines, about symbol counts and whatnot. So having type aliases help me understand what those values are. And also it helps me change my mind easier later on if I decide to use a byte or a long instead. And one of the nice things about a union type is that, at least compared to a class hierarchy, is that you can create a closed hierarchy with only the valid states that your system can have. Whereas a class hierarchy is always open to extension, so someone can either abuse it or introduce other states that you need to handle later on by creating a subclass that a state that you don't know about in your current scope that you're working in. Whereas with a closed hierarchy, you know these are all the valid states that your system can ever have. And since in F#, when you're working fully in F#, you don't have any no's. So that's the number one invalid state that everyone has to think about all the time out of the window. And the whole idea here is to help you make illegal states not representable in your domain so that you don't have to waste time dealing with them later on. Another nice feature that we have in F# is called a unit of measure, where you can decorate a type with the measure attribute. So then you can then start using that type as a unit on your numeric values to add more contextual information to them. And out of the box, the F# runtime, F# handles the combination of different units together correctly. So whereas the 10 meters divided by 2 seconds is going to have a value that has got the unit of meter per second. If you try to combine incompatible units together, you find out compile time that you're doing something wrong. So we can now use this feature to help us model the payouts from our games. So now, if someone wants to create, if one of the game programmers wants to create a payout in coins, and he accidentally passed in a multiplier or 42 as the argument, then he'll find out compile time that he's doing something wrong, because for coins, he's expecting, in this case, in 64, that's measured in pence. And to capture the state for the whole game, we use the record type, which if you haven't seen them before, is just a very lightweight data container type where the fields are immutable by default. And this was one of the, I guess, most complex games that the company has ever done, and it was delivered on time. It did really well for us. And the nice thing about it is that after it's gone live, we had no bugs reported back to me, which was great. So to quickly recap, we've seen how union types and records give you a very lightweight syntax to create types and hierarchies and to help you model your domains very easily, because you can very clearly and concisely express your domain through types. And at the same time, because you don't have to deal with no's, and you can use a union type to create a closed hierarchy of only the valid states that you want to ever deal with. So it helps you make illegal states not representable in your model. And we also saw how you can use unit of measure to give you better static safety with regards to the use of numeric values. And starting from F#5, you will also be able to use them on strings and other types as well. And from our experience, compared to an existing Java implementation for slots engine that powers most of the games for Gamesys' real money gambling games, we saw clearly, easily an order of magnitude increase in productivity with our F# engine. Whereas we have a team of Java developers who takes sometimes weeks to implement a backend for a new game. Right now, by the time I left, I had one guy who I recruited from university who knows a bit of Haskell and no F# knowledge, and he he was able to implement his first game inside the first week after he started with us. And it just goes to show that there's a lot of productivity to be gained there using the right paradigm, the right tools for the job. And that was our first sort of attempt to adopt F# in our stack, and it proved to be a really big win for us. And as of start of October, when I left the company, we had well over 100 games running against our F# backend. And besides social slots, we also make other games, and one of which is a softcore MMORPG game called Here Be Monsters. The interesting thing about this game is that there's tons and tons of content. I think at the end we had about something like 1,500 quests, about 5,000 items in the world, in the virtual world, and just in terms of the dialogue between the non-playable characters and you, there was more text than the first 3 Harry Potter books combined. And we found very quickly that players, well, they like to collect things. They like to go around the world picking apples from trees and growing livestock at home, and occasionally taking their cows through the grinder and make some steak, and then carry that steak around with them so that he can eat it or cook it. So the stage gets really big really quickly. It's not unusual for us to have players whose states are several megabytes big, even after a very short time of playing with us. So when you have really big player states you have to deal with, the stateless approach doesn't make sense anymore because it's very inefficient, it's very slow, and given the size and the number of writes that we are doing, even though we are running pretty scalable key value stores already, you end up paying a lot in terms of the number of nodes that you have to run, taking into account that you need to have redundancy for failure. And serialization also becomes a big cost on your game server, because when you have a player make a call, you have to go and fetch a state, deserialize that state, make some changes, and then serialize it and send it back over the network. You end up spending a lot of your CPU time doing serialization work. And it's not a good idea, it's never a good idea to go to your boss and tell him that you've discovered a black hole in his budget. So in order to make this game work financially, we had to come up with a different way to manage player state. In this case, we decided to go with the stateful approach by taking advantage of the fact that player activities are really bursty. They will come in, do a bunch of things, and then they'll go away, maybe not come back for another couple of days, or they might go make a cup of tea, then come back and do a few more things, and so on. And in the stateful approach, you cut out most of your database calls, as well as all the serialization costs that comes with that. In our case, we can also use S3. We can fall back to S3 because all we need is simple key lookups, and S3 is very cheap to operate and very good for storing large objects. It also has auto versioning or built-in, as well as auto archiving to Amazon Glacier, which is even cheaper long-term sort of backup storage solution that Amazon offers. Internally, in the sort of state management middle tier in our stack, we actually, show of hands, anyone not familiar with the actor model? Okay, sure, couple of hands, that's fine. So actor model is this model for describing computation, and it was coined by Carl Hewitt and his colleagues in 1973. It was later on made popular by Erlang, even though the creators of Erlang didn't actually set out to implement the actor model. They just so happened to have this, very similar ideas around what are the core characteristics that you need when building distributed systems. So in this model, everything is an actor. Actor's got some state and it's got a mailbox. They share no memory. So if one actor dies, it's not going to impact or corrupt the memory for any other actor. And they can only work by communicating with each other using asynchronous message passing. When the actor receives a message, it can create new actors. It can send message to other actors that it knows about. Or it can do some useful things, like do some work, or all of the above. And the nice thing about actors is that they are inherently stress safe, because internally inside the actor, all the code is executed in a single threaded fashion, because messages are handled one at a time. even if they arrive concurrently, there's an arbitrator which creates some ordering for those messages. And in our system, we've got two types of actors: a worker who manages the different states for the player, and he manages them using automatic locking in order to deal with concurrent requests. And after the player's been idle for a little while, he's also responsible for go and save their player state. And there's also a gatekeeper who manages a list of the local workers that we currently have, as well as spawning new ones when a new player comes on board. So here we have worker B and C being live on the server. Player A makes a request. So the gatekeeper sees that, okay, I don't have a worker for this guy, so I'm going to spawn a new worker who then, as part of his initialization, fetches the player state from S3 asynchronously, and then you would reply directly to the request handling code so that it bypasses the gatekeeper in order to reduce the number of messages that have to flow through this guy to reduce the chance of, because this guy, the gatekeeper, is your bottleneck in your system, so you want to reduce the amount of messages that have to go through him. In the meantime, so worker B sees that my player hasn't done anything for a while, so I'm going to save his state in the background asynchronously, and if that was done and no new request comes in the meantime, then I'm going to tell the gatekeeper, and then I'm going to terminate myself. So now if player B comes back after a while, gatekeeper is going to reply with a specific error, which bubbles all the way back to the calling client, who then handles it gracefully by going through the load balancer to find another server to talk to. Because once you've gone with the stateful approach, then you can't rely on the load balancer to distribute your workload anymore. So that was just a mechanism for us to prevent players from hogging servers so that we can terminate those servers when we want to scale down, and also to help us distribute our actual workload. F#'s got built-in support for the actor model through the mailbox processor type, which everybody uses the agent alias. I don't know why that is. One interesting thing to know is that the mailbox processor type is typed, so that we have to define a type for the message that can go to the actors of this type. And in both cases, for a get and a put, we need to specify a reply channel so that the actor can send a response back to the calling code. So now we need to figure out what goes into those guys. Well, we need to tell you if your operation was successful or not, and give you any return value if need be. And if you failed, what was the exception? So in this case, for get request, we need to give you back the current state and version for the player. And for put, we just return unit, which is the F# equivalent of void. And inside a worker, the worker needs to know the unique ID for the player that he's managing. And he has two different states he can be in, either working or closed. And when you start a worker, he's going to fetch the player state and then use that state, and then go into the working state with that as version 1. And in the working state, we're going to asynchronously wait for messages and deal with them. So here we have F# async workflow. So inside this async block, you can do asynchronous operations and bind the return values to a variable using the let bang keyword. Or in the case where there's no return value, you can just use do bang instead. So this allows you to write non-blocking I/O code without dealing with callbacks, and also your asynchronous code looks almost identical to the synchronous counterpart, and it's easy for you to switch from synchronous to asynchronous later on as well. In this case, try receive is going to asynchronous wait for a message to arrive for up to 60 seconds, and this guy returns option type, which is the equivalent to Haskell's maybe, where it's either some value or none. And if we didn't get any message in 60 seconds, then we're going to get a none back, which is now our cue to go and save the player state asynchronously, and then switch to the closed state. When we did get some message back, it's going to come back as some message, which we can now use pattern matching. In this case, we're handling the get message, and we can use pattern matching to get the reply channel and bind it to a reply value, which you can then use to send the current state and version that we know about for this player. And then we're going to recurse and wait for the next message. In the case of a put, again, we use pattern matching to get the state and version number and reply channel out. And because we're doing optimistic locking, we need to check the version number if it matches what we currently know for this player. And if it does, we accept the new state, and then we're going to recurse with that and increment the version number by 1. Otherwise, it means the request falls into this case where the version number didn't match, so we respond with a failure with the version mismatch exception. This just so that when you get concurrent requests coming from the player, either because they're using some bot or using a HTTP proxy or doing something dodgy, you have a concurrent gets that gets the same version and same state back, runs the game logic that modifies the state in some way, and you want to make sure that the first put wins, which is how you can achieve really easily with this. And again, pattern matching allows us to handle all of our branching logic very clearly and concisely. And when we're in the closed state, we're just going to blanket reply, no, except we've stopped working, don't give me any more messages. And compared to the stateless approach, which was just falling under its own weight, the stateful approach, at least we found from our benchmarks, as well as our real production data, that it was at least 5 times more efficient in terms of the same server being able to handle 5 times as much concurrent request as before. And it also cut our average latency down by well over 60%. And we don't have to run database nodes anymore. We can just use S3, which is very cheap and cheerful. And combine that with the cost saving that we're making on the game server side of things, we managed to cut our operational costs down by over 90% and actually made the game feasible to operate at scale. So that was another big win for us in terms of our adoption for F#. So to quickly recap, we saw how you can write a concurrent code without any locks using actors. And another nice thing about an actor is that each actor is a self-contained unit with some explicit messaging protocol. So just like microservices and root aggregates in DDD, this gives you a nice boundary context outside of which everything happens by messaging. So it gives you a nice something that's very easy to reason with. But the built-in support for actors in F# has no support for the distribution side of things, unlike the actors, unlike processes in Erlang. So we had to do some work ourselves, but this was done in 2011, and the tooling is a lot better nowadays. On the .NET side of things, you've got Akka.NET, which is the .NET port of Akka framework from Scala. There's also Microsoft Orleans from the Microsoft Research Group, which was used for the backend of Halo 4. And if you're more adventurous and you want to also just use Erlang or one of the languages that runs on top of the Erlang VM, we actually have a couple of services written in Erlang and running in production as well. But unfortunately, it's one of the things that I never quite managed to push into my team successfully. We also saw how you can use pattern matching to very clearly and concisely handle all of your branching logic, and how you can write async non-blocking IO code without any callbacks using async workflow. And whilst we're talking about async workflow, also want to mention that it's one specific instance of a feature known as computation expressions, which Andreas talked about in her talk early on today. So you can actually build your own workflows. You can write state monads or maybe monads if you want to. And one particular interesting case, application of this feature in F# is this framework called Embrace, which what it does is that it allows you to write a cloud workflow that captures some computation that you want to perform and send it to some machines that you have running in the cloud, operates on them, do all the work, send the result back to you, and then ta-da! You can have a big data crunching job that operates against the gigabytes and terabytes of data, and then just say have a bunch of machines to do all that work, while at the same time programming on your local computer as if you're doing all that work locally. As of right now, it only works with Azure, but I'm actually working on the AWS backend for this, so that hopefully in the not too distant future, you'll be able to run them on AWS as well. Whilst we're talking about heavy monsters, another interesting thing we did for this game is that we've got this achievement and quest system that pretty much ties into anything and everything you can do in the game as a player. So, for example, if you were out monster hunting, you caught the gnome, you're going to get some reward for that, and you can make progress on any quest that requires you to go and catch a gnome in the world. And when you get XP, you might level up, and when you make progress on a quest, you may complete it if it's the last thing that you need to do. And when you complete the quest, you're going to get more rewards, and you're going to make more progress in other quests, and you're going to unlock new quests, follow-up quests in the storyline. And when you level up, well, you're going to get more rewards. You make progress on quests, you unlock level locked quests, and the whole thing also feeds into the achievement system. And guess what happens? You're going to get more of everything. So this system actually works quite well. It's really easy for us, for our game designers, to go and build really interesting quests because they have access to pretty much anything the player can do and add all kind of tweaks and triggers. But it was a nightmare for me to implement. For starters, we've got over 100 different actions that distinct actions that you can perform in the game. Many of them will give you some kind of reward, and all of them can be triggered by one user-generated request. We have to go through and handle all of that recursive loop, and then at the end of it, collect all the delta, all the changes in the player state, and reply that and send it back to the client in the response. So having this kind of system just makes my job much harder. And what makes it worse is that a lot of these changes are happening from different abstraction layers that depend on one another. So you've got abstraction layers for managing, leveling up, for fishing, monster hunting, or traveling. And on top of all of that, you've got analytics tracking. We record everything you do as well as all the state changes that happen as a result of what you're doing in the game, so that we can later on for support understand what's happened. So think of it as event sourcing, but we don't quite use it in the same way. And also, if you as a player come to our game through one of the ad agencies, so if you click an ad on Facebook or on your mobile devices that took you to our game, then we also need to inform those ad agencies when you've reached certain milestones so that they can optimize the algorithm on their side to help bring better players into our games. So all of these things have to also tap into the same stream of events happening, which again just made my job even harder. And the solution that we came up with was inspired by the message broker pattern, which is an architectural pattern that we've just applied at the lower level, where anything interesting happens, we record it as a fact, and then it's put inside a queue that's specific to this user request. So each fact gets processed by a number of different processors for different aspects of the game, who may choose to ignore them or do something. And because they choose to process it, they may cause other state changes or trigger other interesting things from happening. So all of those then gets added to the queue, and they'll have to get processed in turn. There's quite a few slides for this. So the big downside for this, actually, I need to talk about something else first. So we actually consider a number of different other approaches, including just using a complex event processing system, and there are quite a few of them available. But for us, the purpose and the scope of the events are really local and really specific to that one user request. And what we really needed was a way to linearize what is otherwise a spaghetti application flow, and which is why we ended up settling for a tailored solution for our use case, which in hindsight is actually fairly easy to implement and quite lightweight, both in terms of the performance overhead and as well as the amount of the cognitive overhead that we incur when we're trying to manage the system. The big downside is that we needed to have lots of facts. We need a fact for every single user action you can do, as well as a fact for every state change that can result from those user actions. And if I was to do this in C#, it would probably take me, I don't know, weeks of just sitting down, being really bored, writing classes, copy and pasting everywhere. That is if I don't sort of shoot my face itself in the face first, or just rage quit. So in the end, I decided to just do it in F# and using, again, unions. But then when you have a union with 100 different cases, it doesn't, it's not any more manageable either. So what you would do normally in this case would be to break it up into union types for specific areas of the game, and then just nest them in a top-level type. So now, and that would be the idiomatic way of doing things in F#. And now, so when you want to process a fact, you just pattern match it against that. And for each of the nested cases, have some specific chunk of code that does the processing. But then C# strikes back. Because most of our game logic is written in C# as well, and when you're in C#, you want to create a nested fact. That's the kind of code you end up writing, which gets really ugly really quickly. So we decided to reach for a compromise and use a marker interface instead. So now our processing code is still kind of similar to what we had before. Instead of just doing pattern matching against the nested types, we use a type test instead. So this removes from having a top-level union type. But because we've done that, it's now possible for us to have invalid state or states that we don't know about at the time when we write this later on. So we need to have a special case handling for that. But even with the compromise that we've settled for, this was still really easy. It's quite a simple system, and it was easy to reason with, and it was easy to change and add things as well. So whenever you want to make a change, you typically just make the change in the domain type and then just follow the compiler errors to fix all the places that you've broken. And it saved me loads of time, both in terms of the time you spend implementing the system, as well as the time it takes to maintain it and improve it going forward. And as the name suggests, heavy monsters, the large part of the game is about monster catching. That's a shame, you can't just see the monsters here. It's part of the logo. So in the game, we got this thing called an almanac, which is like an in-game Wikipedia, where you can look up different things, you can find the world. In this case, you can see that Bigfoot lives somewhere in North America. He likes the alluring goat, and you can catch it with that particular trap, as well as your different chance of success for each of these things. So now we got this challenge where, okay, we want to automate a process of calculating the stats for the monsters and the traps, having had a game designer have got some rough idea of what the catch rate they want between a monster and a trap using the formulas that we've derived. And it used to be that the game designer would do this by hand via trial and error, where they've got some rough ideas, say, I want to be able to catch the Bigfoot with the musketeer trap at roughly 75% of the time, and then knowing the stats for one of these things, tweak the other stats for the monster until he gets a number that's close enough to what he wants. But of course, when you've got a system that forces people to do this kind of thing, which is obviously very laborious and also error-prone, what you're doing is you're really just hanging your game designers out to dry, because as Brian Hunter said really well this year at the NDC Oslo, that if you require constant diligence, what you're really doing is you're setting everyone up for failure and hurt, because people's going to make mistakes, right? They're going to make mistakes over and over. Hopefully not the same mistake over and over, but human errors are inevitable, and you have to deal with that. So instead of having our game designers spend all their time doing this kind of manual work, we decided to write a number of genetic algorithms and then just expose this as a web tool to them, where they can choose the trap they're working with and what target they want for each of the monsters, and then give us some error margin that we need to accept, and then press a button and wait for answers to come back. And is everyone happy with genetic algorithms? Anyone want me to go over what genetic algorithms work? Okay, cool. So that's another case where we found F# to be really useful in terms of helping us automate some of the sort of challenges that people tend to come up with all the time in sort of game design area. Okay, so moving on. So as I mentioned earlier, we use Amazon Web Services very heavily, and the last time I did a count, we were using about 28 different services, which over the number of years I've been working with them, I've seen a number of hidden complexities from the APIs often is when the API is exposing some underlying complexity with the operation that you're performing. And if you look at some of the documentation, for example, you see a long page, you just keep on scrolling and it just goes and goes and goes with all the different options that you can tweak and whatnot in those APIs. And rather than exposing all of that to our developers, what we have done is write simple DSLs to encapsulate and hide a lot of these complexities. And it turns out F# and function programming languages in general are really good for writing DSLs. One of the examples we did was with Amazon CloudWatch, which is a monitoring service that Amazon gives you, which collects metrics from your EC2 instances or your usage level of the different services that provide. But you can also publish your custom metrics as well. And it gives you a little web management console where you can compose different graphs together, and you can overlap them, then choose over different time ranges to help you debug, work out what's happening in production. But one thing it doesn't have is a built-in way for you to find correlations between different metrics, which is something that you tend to do a lot when you're doing post-mortem after some incident has happened. And so if one of your payment services was slow last night and you want to find out what was the root cause for it, was it because the database course was slow or some other service that we depend on, say Google Payments or PayPal or whatever, you have to go and to dig through all the metrics yourself and trying to figure out what actually happened. And when you've got thousands of raw metrics that we do, the amount of work required is just insane. It's not even funny. And it's what I would call a pain-driven development. And so we did this a lot for over a long time, and it's until eventually I decided to just spend a weekend and deal with it. And that's when I wrote two very simple DSLs. One is internal, one external, which allows us to say take queries like this one, where we want to find metrics whose 5-minute average was more than a second any time over the last 12 hours, into an internal DSL that's really human readable, or something that's even closer to English as an external DSL, which you can also use via a command line interface. And similarly, if you want to find out if any of your cache nodes had a CPU spike, you can write something that targets specific namespaces in your metrics, or just using metric names, using regex. In all, there's about 15 different operators that you can use on both the internal and the external DSL. And the internal DSL was written in about, 25 lines of code with some supporting functions that's shared with the external one, which is implemented using a feature in F# called active patterns. But all in all, it wasn't a lot of code either. But I did make the rookie mistake of starting to work on this at about 2 a.m. Luckily for me, I get everything done in about 2 hours, because by then it was 4 o'clock, and that was the first time I was able to compile my code, run it up. Surprise, surprise, everything worked and did exactly what I was expecting it to do, which was great. And when I went back to work on Monday and told my friends that, hey, I did this, look at what I've done this weekend. Now we don't have to do all this manual work anymore. They just said, oh, wow, you type really fast to do that in 2 hours. But really, using F# is using the right tool for the job gave me all the advantage that I needed. So quickly recap, we looked at the Amazon CloudWatch and how this impedance mismatch turns routine, so post-mortem activities into an exercise of finding a needle in a haystack, and how you can write using F# or any other language you want to write DSLs that makes that needle that much easier to find. We actually, so I should build a number of other different DSLs for working with Amazon. Another one is for Amazon's DynamoDB, which is still the fastest growing service that Amazon has to this day. If you haven't heard about it, it's manage the key value store with built-in 9/9s, with built-in redundancy and 9/9s guarantees, and also it's give you really good, amazing performance. You're looking at get and put at 2 to 3 milliseconds average, because everything runs on SSD, and it almost never goes down. In the 4 years I've been using it, it's only gone down once, and that happened last month. And I actually did a talk. I just gave this talk I think like a week after that happened. So that was standing there says, "Oh, it never goes down," and it just went down last week. And one of the interesting things about it is that unlike most of the other services that you use with Amazon, where you pay for your usage, with DynamoDB, you actually go to Amazon and say, "Hey, Amazon, I need a database table that can handle 10,000 reads a second and 5 gazillion writes a second." And Amazon would just go away, "Yep, sure. I'll reserve all the capacity I can to handle the throughput that you're asking for, and you just pay me for the amount of resources that I have reserved for you." So it gives birth to some really nice, very interesting use cases. So I know of this advertising company that does no traffic almost all year round, except for 4 hours of Super Bowl, during which they're getting some ridiculous numbers like 4 million writes, so 4 million reads a second for that 4 hours. And they ought to do the whole thing, scale up the databases through the roof for that 4 hours before Super Bowl starts, and then scale it all the way back down after it's done, and just pay a couple of $1,000s to get the whole thing over, rather than having to invest I don't know how many millions of dollars into super scalable and flexible infrastructure that can handle that kind of peak load and not use it for 99.9% of the year. So DynamoDB is amazing, and if you're on Amazon, this is by far the most common thing that everyone uses, which is also why when it did go down last month, it took down a huge portion of the internet. Netflix was down, Fortran, a bunch of other, and our games, and pretty much every other game that I play on my mobile, they were all down because everyone that was on Amazon was using DynamoDB, and because it's never gone down, everyone just assumed that it's never going to go down, which is a painful lesson for everyone to learn. The one downside you have with DynamoDB is that there is no built-in query language, or at least there wasn't. There is something now, but it's still not that great. So to make a simple query, end up writing code like this, which is actually not that bad. The problem is that once you've read everything you're doing, so at the end of it, where you're making a query, I kind of forgot what was the thing that I was trying to do in the first place. Because remember, in psychology, you've got this 7+2 rule that says we can only keep a very small number of things in our head at the same time. So that wasn't great, and having to use DynamoDB all the time and having to write code like that again all the time, which means I had enough pain and have to go and do something about that. So I wrote a sort of SQL like DSL, which help us discuss some of this complexity with DynamoDB, and allows us to write something that's SQL, that's very similar to SQL, so that people coming into the team who doesn't know DynamoDB necessarily is able to understand very quickly what it is that we're trying to do with those queries. And ultimately, with the DSL, very simple, like you do with most language parsers. You take a query, you pass it into your abstract syntax tree. In this case, instead of turning it into some other code that JavaScript or whatever, you turn it into something you can execute against DynamoDB service. And for this, I actually use the fparsec, which is the F# port of the parsec library from Haskell. And it's a library that allows you to to write very small parsers for small simple things like a string or floating point or equal sign or whatever, and then compose them together to make more complex, more complete parsers for your query. So now I can take what I would normally write like this into something that's much more expressive, more the question that I'm trying to ask my database for. And again, the whole query syntax parser was written in about 50 lines of code, because you get great productivity from using tools like F# and tools like fparsec. And the last thing I want to show you is something that I wrote to work with Amazon S3. It's using a feature from F# called a type provider, which came out of F# in F# 3, where I can create a type that represents my Amazon S3 account, and every time I press dot, it's actually making a call in the this is within the F# repo, where every time I press dot, it's actually making a call against Amazon S3, and based on the data that comes back, it's generating types on the fly so that I can get the IntelliSense support against my buckets and objects in my S3 account. And you can also, hold on, you can also create a type that represents a search in your S3 bucket, in S3 using prefix, which is very useful when you've got the buckets of player states that's got millions and millions of objects. So again, when I press dot there, the IDE is making a call to Amazon S3, doing the search, and based on data that comes back, generating those types on the fly, which just makes my sort of day-to-day operational work, ops work, a lot easier, because we do work very heavily with S3. And using type providers like this is great, because it removes all this magic string from my code and allows me to do everything I need to do against S3 form within Visual Studio without having to open up some other tool that I have to pay for, so that I can do a search in S3, grab some objects, download them, write some code, parse it, read it, do some stuff, and then go back to the tool and put it and upload it back onto S3. Now I can just do all of that from within Visual Studio. And we don't have to deal with any code generation myself, and because all the types are generated on the fly, they actually get erased to the object type at runtime. So you can easily have millions of generated types at runtime without blowing up the CLR, which is why you've got the type providers for things like SQL Server, for a number of other things that you can create a new type for every single row that you have in the database. So that's all the that's a sort of like a quick run through of the different use cases that I had for F# in my day-to-day job, or in my old day-to-day job. And I hope it's giving you a taste of what are some of the sort of real-world use cases that the function programming is really good for, and how you can get some really nice benefits from using F#. And yep, thank you very much for listening. Has anyone got any questions? Yeah, Alfonso?
Actually, I wanted to make you the question you made us before, that you said that whether we should use it if we want to promote
Oh, yeah, yep.
our companies. And first, I think this presentation is great. I think it's a very good example of how to use F# functional programming. But do you think this is more for programmers or project managers? Or do you think this will be also useful for project managers?
For project managers? Yeah. Okay, one of the things I didn't show you is that for those slots games where we have the F# code, we have every game's got a bunch of model for this that describes the symbols, how to lay out, and all that stuff. And those F# code is really quite human readable. It's quite easy to read, even if you're not a programmer. So I actually gave those to our mathematicians, as well as with some tooling, so that they can tweak the numbers and then use the tool to run, say, a 10 million spin simulation to see whether or not he's getting the right metrics. For the slots, for the real money gambling slots, at least, you've got this requirement by the regulators that say at least 95% of the players' wager have to go back to them over the long term. So that's called RTP. And measuring RTP is quite an important thing for those guys. So having this ability for them for me to give them some code where they can easily understand without necessarily being an expert in programming, and being able to validate their changes very quickly, that was quite useful as well. So yeah, it's not just for programmers, just because the language itself is quite simple syntactically. But yeah, go.
The DSLs then is, you think they are very useful to communicate between programmers and also other parts of the team, like these mathematicians or?
No, for the DSLs, they're more for us. But if we have got a bigger team where you've got people dedicated to doing ops side of things, so DevOps or whatever you call it, then yes, that would be useful for those guys. But for our team, because it's a very small team, we only have, by the time I left, about 6 backend developers that's split across multiple games, and we do everything. So we don't have a dedicated DevOps team, and we do all of that ourselves. But otherwise, the DSLs will be useful for those for DevOps team as well. But even then, you kind of alleviate some of the complexity that other people have in other games have to do in order to find some metrics they're looking for. So you can turn those into queries that you can run from your CLI tool and encapsulate some of the sort of common things that people do and expose them via your tools as well. So yeah, it's possible for you to just expose the DSL to other non-programmers.
Sorry, another very quick question. When we are talking about functional programming, we are talking all the time about immutability. So
right.
sometimes we think that this means that we cannot use state at all. But you have been talking a lot about the state. So the conclusion would be that we shouldn't be afraid of state. We just need to use the right tools for it.
Yeah, that's one of the things that when people, I guess in the F# community, you keep hearing people saying functional first as opposed to just functional only. I mean, having state and having immutability is great. We all know that. We all here at the Lambda conference. But I think it's more important to choose immutability as default, but go mutable where it makes sense, where it's pragmatic, for example, rather than being everything has to be pure all the time. At least that's my take on things. We're all there trying to get something done, and that's the important thing. Immutability helps us do things better in many cases, which is why it should be the default, but it doesn't have to be the only way we solve problems. But yeah, we do use mutable states a lot of places as well. Okay, cool. Well, thank you very much.